So there's a good argument that life would only form in those particular pocket universes that happen to have vacuums in them, which have incredibly small vacuum energies. And when there are this many vacua to choose from, even if the vacuum energy has to be incredibly smaller than average, if you think of these vacuum energies as just being spread over the range of values, there would be plenty that would have this incredibly small vacuum energy. The only problem is to explain why we should be living in such rare universes. And the explanation would be, if this is right, prizes at the National Academy are chosen by committees, while the membership is chosen by the entire membership. So maybe a question of a different group that one has to avoid having any enemies within. Certainly there was some sense, I'm sure, that people were jealous of Carl because of his enormous popularity on television and on the Johnny Carson show and so on. I did want to highlight, screen lights up in the slides. I did want to highlight one particular example of what I think is what's called Sagan's extreme ability to find ways of driving points home in an emphatic way. So one book of Carl's, which I like very much, The Dragons of Eden, written in 1977, begins with chapter 1, in which he tries to impress the audience with how incredibly recent everything that we know about the history of the world is compared to the lifetime of the universe. And he did this by taking the age of the universe and mapping that into one day, and then specifying on all various events of geological and cosmological human history happened. And his list was much longer than what I'm quoting here, but a few examples of the things that he listed is that the first humans don't appear until December 31st at 10:30 p.m., just an hour and a half. Of the last hour and a half of the history of the linear history of the universe. It was kind of incredible. And the alphabet only comes 10 seconds before the end of the year. Euclidean geometry comes 4 seconds before the end of the year. And the widespread development of science and technology, those are follow words, came within the last second. He really just left us blank. Within the last second, which is kind of amazing, I think. So I thought this was striking and a very visual way of getting across this incredible discrepancy in timescale between what we think of as human history and what cosmological history is about. Okay, with that, I will move on to talk about the main topic of my talk today, which will be inflationary cosmology. But I want to start by giving a prelude of what I'll call the standard Big Bang, and by that I mean the standard Big Bang before inflation came along. Inflation now is really considered part of the standard cosmology, but here I mean before inflation. It's the theory that the universe, as we know it, began some 13 to 14 billion years ago, and now we have a pretty precise estimate, 13.80 plus or minus 0.2 billion years, coming from the Planck satellite collaboration. It's a theory that the universe, as we know it, began at this time. Now, I do want to emphasize these words, as we know it. We don't really know what happened, if anything, before the Big Bang. I'm sure there are many books you can read that would say the universe began with a singularity at that time. There's a simple theory of that type, but we don't really know at all. And I might add here that one of the things I was impressed by with Carl Sagan's Dragons of Eden is that he also discussed the Big Bang, and also was clear that we know something dramatic happened in 13.8 billion years ago. Actually, it's 15 billion years ago by his estimate in 1977. But we don't really know that was the beginning of time. It's really just the beginning of what we understand about time. And I think it is a very big thing in science, not to overstate what we actually know. I think that tends to cause people to stop believing what we're saying. So, the initial state, and by that I mean the state 13.8 billion years ago, was a hot, dense, uniform soup of particles that filled space uniformly and was expanding rapidly. The conventional Big Bang theory describes how the early universe expanded and cooled, and those are actually very simple calculations that can be done rather quickly in my elementary course on cosmology in 1886. It also talks about how the light chemical elements form. That's a more complicated story. I should emphasize here that the reason that question arises is that this model starts to describe the universe at a time when it was so hot that even the nuclei of atoms would not have been stable. They would just been ripped apart by the heat. So all of the nuclei that we see in the universe today have to have evolved since the Big Bang. We now believe that only the lightest of those chemical elements were produced in the Big Bang, but we can calculate the expected abundance based on the Big Bang theory, and it works quite well. Most heavier elements, really everything heavier than lithium, we now believe were produced not in the Big Bang, but much later in the history of the universe in the interior of stars. And then stars undergo supernova explosions, spewing these heavier elements out into space, ready to recollect into later generation stars like our sun and solar system surrounding those stars, and that's what makes up all the material that we see around us. You very likely have heard Carl Sagan's famous phrase about how he describes that: "We are made out of star stuff." Favorite slogan of Carl's. The theory also describes how matter congealed to form stars, galaxies, and clusters of galaxies. This is to some extent still a work in progress, but it certainly does seem to be working out quite well, and we do understand a lot of the details of how that works. I want to focus though on what the classic Big Bang theory does not describe, because that's really where inflation comes in. It says nothing about what caused the expansion. The Big Bang theory really only describes the aftermath of the Bang, in spite of the fact that it's called the Big Bang theory. It's not really a theory of the Big Bang at all. It also says nothing about where all the matter came from. In the conventional Big Bang theory, for every single particle that exists in the universe today, there was at least some precursor particle that was there from the very beginning, being the time at which this theory starts to describe the universe. In other words, the Big Bang theory really says nothing about what banged, why it banged, or what happened before it banged. It's a truly bangless theory. And inflation to some extent fills in some of those gaps. Okay, so what is inflation? Inflation is essentially a prequel to the conventional Big Bang theory. In particular, it's a theory about what created the bang of the Big Bang, what propelled the universe into this period of enormous expansion. Inflation is also a possible answer to the question of where all the matter came from, or at least where almost, at least where almost all the matter came from. Inflation requires a few grams, perhaps, of initial matter to get inflation started. Inflation does not explain where that came from. We need some other theory for that. But inflation can take just a few grams of matter and build a whole universe from it. So inflation is not a theory of the origin of the universe, but it can explain how the entire observed universe emerged from a tiny patch that might have been about 10 to the minus 28 centimeters across. Maybe I should put this in perspective by reminding you that the size of an atomic nucleus is about 10 to the minus 15 meters. So this is vastly smaller than a single proton. The initial universe could have been that small, and with a mass of just a few grams. It would be incredibly dense, of course, to be that small, and still throw a few grams of matter in it. Inflation explains what drove this expansion in terms of gravitational repulsion. Now, gravitational repulsion is something which is very likely something you haven't heard of before, although maybe you have. It's certainly not the way Newtonian gravity works. Newtonian gravity is entirely attractive. Two masses always attract each other, with of course proportional to the product of the two masses and inversely proportional to the square of the distance between them. So where does gravitational repulsion fit in? Well, I like to describe the underlying physics behind inflation in terms of two, what I call miracles of physics. Now, since I'm talking to the secular society, I should maybe point out that I know we're not supposed to believe in miracles. Secularism is all about, I imagine. But what I mean by a miracle of physics is something that's special. A miracle of physics is actually a feature of the laws of physics as we know them. Also, I would not count it as a miracle of physics. To be counted as a miracle by my standards, it should have two properties, and I'll argue that the two things I'll tell you have these properties. One is it should be something that I wasn't taught when I was a student, so it's novel. And secondly, it should be something with far-reaching consequences that can really change our picture of the universe. And I'll be talking about two miracles of physics, that I consider to be miracles of physics by these definitions. And the first of which is this notion of gravitational repulsion. As I said, it's certainly antithetical to Newtonian gravity, which is always attractive. But really, since the advent of general relativity as a theory of gravity, we've known that gravity can act repulsively. The next line, you notice, is kind of a light type. That means that if you can't follow a word of it, it's okay. You won't really need it, but it's extra details. In general relativity, the important feature that gives rise to this possibility of repulsive gravity is that in general relativity, it's not only mass densities that create gravitational fields, but pressures can also create gravitational fields, something far into Newton. And pressures can actually be positive or negative. A negative pressure is a suction. If you take a piece of plastic, say, and pull it outward, it will pull back. That's a negative pressure, not big enough to create a noticeable gravitational field, but that's an example of a negative pressure. It's really something that's fairly mundane. It turns out that positive pressures create attractive gravity, but negative pressures can create repulsive gravity. And that's the secret of repulsive gravity in general relativity, and it's the secret of inflation. Einstein, in fact, used this negative pressure gravitational repulsion option in his original cosmological model from 1917, the model where he introduced this thing called the cosmological constant. What happened was that Einstein realized that if the universe were described as just a static configuration of mass filling all of space, it would actually collapse under the force of ordinary gravity. He discovered it in the context of general relativity, but we believe, and actually Einstein realized himself, that the same thing would actually happen in Newtonian gravity. Newton talked himself out of it. He did think about that, and came up with the wrong answer, one of the few wrong answers that Newton came up with. To avoid this problem of collapse, Einstein introduced this cosmological constant, which we really view as a background vacuum with a negative pressure that produces gravitational repulsion. And he adjusted it to be just right to balance the attractive force. So it was a very fine-tuned model, but people didn't worry much about fine-tuning in those days. Now we worry about that more. It seems improbable that there could be such a fine-tuning. Modern particle physics suggests that at super high energies, there should be a lot of possible states of matter with large negative pressures that would create the kind of repulsive gravity that inflation needs. So in the context of what I should call extrapolations of what we know about particle theory, this all seems very natural. That it could easily be a negative pressure material, repulsive gravity material in the early universe that can drive inflation. So inflation proposes that a patch of this repulsive gravity material existed in the early universe. If inflation arises from what are called grand unified theories, then we can make an estimate of what the energy scale would be. The energy scale of grand unified theories is about 10 to the 16 GeV. I guess I'm finding GeV, that's the mass of a proton. If inflation happened at that energy scale, this patch would only have to be about 10 to the minus 28 centimeters across. I should maybe clarify that we don't really know at what energy scale inflation happened, so there are other possible answers to this question. They would all sound about as absurd as this answer sounds, though, so it probably doesn't matter much. That is, that size of the initial patch would be unbelievably small. This patch is then enlarged fantastically by inflation, so even if such patches are incredibly rare, it doesn't matter. Inflation will make them big enough to come to dominate the universe. The gravitational repulsion created by this material then provides this expansion effect on the patch, causing it to grow exponentially with time. And again, using numbers from grand unified theories as an example, the doubling time would be only about 10 to the minus 37 seconds. And 30 10 to the minus 37 seconds, just region to double in size and then double again and then double again. The patch needs to expand exponentially if it's going to become our universe. Needs to expand by at least a factor of 10 to the 28. Remember, it started at 10 to the minus 28 centimeters, so it has to end up with about 1 centimeter across. And that requires about 100 doublings. And 100 doublings at 10 to the minus 37 seconds each only requires 10 to the minus 35 seconds if you do that multiplication. And at the end of that, the universe has a size of about a centimeter, about the size of a marble. And when I said use the word universe, that's a little bit of an oversimplification. I wrote it more accurately on the slide. The region that's going to evolve to become the presently observed universe has to have been at this time about 1 centimeter across. We have no idea how big the whole universe is now or then. So we don't want to talk about the size of the whole universe. We don't know anything about it, except maybe bigger than this. If you see it is right. Now, inflation ends eventually because this repulsive gravity material, this driving the accelerating expansion, is unstable, like radioactive substances, so it decays. By decay, I just mean it converts into a more normal kind of matter. And when it does decay, it releases the energy as it's locked up inside of it. That energy forms a hot, dense soup of particles. In fact, the hot, dense soup of particles that seems to have exactly the same properties as was assumed to be the initial condition in the conventional Big Bang theory. So the briefing ends, inflation creates this hot soup of particles, and standard cosmology then takes over. So inflation does not contradict anything that had been believed in the context of standard cosmology. It just provides a prequel that sets up the initial conditions that previously had been assumed. A caveat here, the decay that I talked about here happens randomly, so it doesn't actually happen everywhere at once. And that will be important later when we talk about how inflation can lead to a multiverse, which is one of the themes of my talk tonight. So we'll come back to that. An important feature here is that after this repulsive gravity material decay, the universe just continues to coast right up to the present time. A very important feature, though, is that during this exponential expansion, when the universe expanded in radius by a factor of 10 to the 28 at least, it's very important that the matter inside that region did not thin out. Rather, this repulsive gravity material behaves very peculiarly. As it expands, the density of it is not lowered at all. So at the end of this expansion, we have a ball that's now 10 to the 28 times bigger in radius than it was, and a cube of that in volume. It still has the same density that have been started, which sounds like it ought to be impossible. Seems like it must violate conservation of energy. And as you might suspect, since I told you there were two miracles here, we need a new miracle to explain why this does not violate conservation of energy. So even though more and more mass or mass energy appeared, as this impulsive gravity material expanded, total energy was in fact conserved. And how did that happen? Well, we needed a miracle, miracle number 2. So what's miracle number 2? You might think I'm leading up to some statement that energy isn't really conserved. It turns out that's not the case. As far as we know, energy is exactly conserved. But the catch is that energies are not always positive. We tend to think of energies as being positive, but they're not. And in fact, the energy of the gravitational field is negative. And that fact is even true in Newtonian physics, by the way, and it's also true in general relativity. And inflation takes advantage of this fact in a big way. So what happens during inflation is that the negative energy of the gravitational field that fills this ever-expanding region exactly cancels the positive energy of the extra matter that's being created to fill this region. So the total energy adds up to something very small and is consistent with being 0. It's quite possible that in our universe, a huge positive amount of energy in matter and radiation, all the stars and galaxies and everything, that huge positive contribution is very likely canceled by an equally huge negative contribution of gravity, the energy of the gravitational field that fills the universe, and the total is consistent with being just plain 0 for the total energy of the universe, which I think sounds kind of miraculous to me. It's like you think of the universe as being a huge thing with a huge amount of energy, but really, it's probably 0. In any case, it's certainly very, very small. So that's miracle number 2, and explains how inflation can build an entire universe, starting from a little ball that's 10 to the minus 28 centimeters across and a few grams of mass. Okay, so far I've told you kind of the story of inflation. I've tried to tell you what the scenario looks like. Now I'd like to say a few words about evidence that our universe actually did this, that this actually very likely is the history of the universe in which we are living. So I want to talk about 3 pieces of evidence, the first of which is the large-scale uniformity of the universe, the fact that it looks the same in all directions. The strongest evidence we have of this fact comes from the cosmic microwave background radiation. This is radiation which arrives at Earth from all directions. It was discovered in the 1960s. And it has now been measured very, very accurately across the sky. And what we found is that the intensity of this radiation is the same in all directions to an accuracy of a few parts in 100,000, which really is incredibly uniform. And that fact becomes particularly perplexing if one thinks about what would be needed for that to arise in the context of standard cosmology. Now I mean standard cosmology without inflation. Without inflation, one has to reckon with the fact that this radiation was released at about 400,000 years into the history of the universe. And by released, what I mean is that prior to 400,000 years, the universe was filled with a hot plasma. That is, the electrons were ripped off of atoms, and we just had protons and electrons mostly floating through the universe as free particles. And a plasma like that is very opaque, very non-transparent to radiation. So during this first 400,000 years of the history of the universe, the radiation, even though the photons were individually traveling at the speed of light at any instant, the photons were constantly bouncing off of electrons and changing directions, doing a random walk, which in fact gets them essentially nowhere during the first 400,000 years. So you can think of the photons as really just being frozen, stationary for the first 400,000 years. And then, according to our calculations, the universe at that point cooled enough so that the atoms neutralized, and a neutral gas of hydrogen or helium atoms is very, very transparent to photons. So at that point, the photons that now make up this cosmic background radiation started to free stream. They just traveled along straight lines. And then, just like the light traveling from my face to your eyes along straight lines, that you see what I look like, the photons starting to free stream at 400,000 years, traveling to our detectors today, gives us an image of what the universe looked like at 400,000 years. We really have essentially a photograph of what the universe looked like at an age of 400,000 years. And what it shows is that the universe was uniform to this incredible accuracy, few parts per 100,000. Furthermore, we can ask if the universe started out at what we call time zero, what we call the instant of the Big Bang. If the universe was not uniform then, what would it take for it to become uniform by the 400,000 year mark where we're measuring it? And the answer, this is really the killer point, the answer is that energy would have to travel about 100 times the speed of light to smooth the universe out that quickly, if it didn't start out smooth. So there's an assumption here. The universe, perhaps for reasons that we don't know anything about, started out exactly smooth. Then there's nothing to solve here. But we don't have any such theory. A theory that we have is much better than a theory that we can expect, so we can only speculate might exist. So inflation is a possible answer to this question. Inflation solves this problem simply by the expansion that we're talking about. If we look at the inflationary picture of the evolution of the universe and say follow it backwards, the universe, say, now is this big, the distance between my hands, and we'll follow it backwards in time. It gets smaller and smaller and smaller. But eventually we come to the time at which inflation ended. And to go back further, we're now going to follow the universe through this inflationary period. The inflationary period is a period of enormous expansion going forward in time. So going backwards in time, it's a period of enormous contraction. So if you continue to follow the universe backwards from here, it gets tinier and tinier and tinier. And at the start of inflation, it was just unbelievably small. Well, we already talked about that. 10 to the minus 28 centimeters or something like that. While the universe was so small, there was plenty of time for it to become uniform in temperature and mass density and everything by the same processes which cause the air in this room to become approximately uniform in temperature and uniform in density throughout the room. And then inflation takes this tiny speck, which is already uniform, and stretches it to become large enough to include the entire observed universe, and it maintains the uniformity as it stretches. And that's how inflation solves this uniformity problem. So that's all I want to say about that. I want to move on now to problem 2. I told you it would be 3. 2 is what's called the flatness problem, which can be summarized by the question, why was the early universe so flat? Then you have to ask, what does flat mean? Flat does not mean two-dimensional, I should emphasize here. Flat refers to the geometry of space, which, according to general relativity, does not have to be Euclidean. General relativity is really based on non-Euclidean geometry, geometries in which three-dimensional space can bend and twist and stretch. And the question is, why was the early universe so close to flat? Now, if we assume, and I'll make this assumption for now, if we assume that the universe is, as we observe it to be, homogeneous, meaning the same in all places, and isotropic, meaning the same in all directions, then there are only 3 possible geometries, and those are closed geometry, which is like the surface of a sphere, that's really a 3-dimensional geometry we're talking about. It could be an open geometry, which is like the surface of a saddle, or it could be the flat geometry, which is really just in between those two. The flat geometry is the Euclidean geometry that we all learned in high school. And we know that the universe is indeed very close to flat. That's why we learned Euclidean geometry in high school. We all did, right? That's what they taught us. Okay, so cosmologically, this flatness is measured by a parameter labeled by the Greek letter capital omega, which is the actual actual mass density relative, divided by what's called the critical mass density. It turns out that the geometry depends entirely on this parameter omega, the mass density of the universe. If omega is equal to 1, if the mass density is equal to the critical density, that's by definition the density that makes the universe exactly flat. If omega is bigger than 1, it's closed, or omega is less than 1, is open. Okay, so this is mainly really just vocabulary for now, but it does involve the important physical statement that the curvature is determined by the mass density. Now, how does the mass density behave as the universe evolves? The important point which drives this problem that we're talking about, the problem called the flatness problem, the important mathematics behind it is that omega equals 1 turns out to be an unstable equilibrium point of the equilibrium of the evolution of the universe. And that might be a fancy word. What it means, simply, is that if omega is exactly equal to 1, the universe will be flat and stay flat forever, and omega will stay 1 forever. But if omega is just a little bit bigger than 1, it will rapidly start to rise, and in fact go off to infinity. And if omega in the early universe is just a little bit less than 1, it will rapidly trail off to 0, and the universe will just be essentially empty. All the matter will scatter out. To be even within a factor of 10 of the critical density, which is what was known in the 1980s. I'm trying to sort of take us back to when these arguments were first made. In order to achieve that degree of closeness to omega equals 1 after this evolution, omega had to start out at 1 second after the Big Bang, equal to 1 to 15 decimal places. So it requires an incredible amount of what cosmologists refer to as fine-tuning. Fine-tuning means some parameter has to be chosen to have a very specific value, or else it just doesn't work. And furthermore, we have no reason to know, or believe, or understand why omega should start out so incredibly close to 1. So this is what's called the flatness problem. Inflation gets around it beautifully. Inflation, we know, changes the behavior of gravity. It causes it to become repulsive instead of attractive. And that also changes drastically the way that omega evolves in time. And in fact, it completely reverses it. During inflation, instead of being driven away from 1, as omega is during all the other periods of time, during inflation, omega is driven towards 1, driven towards 1 incredibly rapidly, actually doubling exponentially fast. That is, omega minus 1 falls off like 1 over the square of the expansion factor. So inflation drives omega to be 1 incredibly quickly. Now, since it drives it so quickly to 1, we expect, unless inflation is itself fine-tuned, to just stop as it's approaching 1. The expectation is that omega today should be incredibly close to 1, far closer than we can measure. So there's a prediction that omega should be 1 today. Now, historically, that used to be a problem before 1998. Before 1998, most astronomers, it's somewhat controversial, but most astronomers thought that omega was 0.2 or 0.3. Might mention a personal note here that during the 1990s, it was fairly uncomfortable for me to have dinners with astronomers, because they would sneer and say, yeah, inflation is a beautiful theory, we agree that it's beautiful, but it can't be right because we know that omega is only 0.2 or 0.3, and inflation predicts that omega should be 1. Fortunately for me, and I think also for anyone who likes to have a simple theory of the universe, that all changed in 1998, and now the best value of omega is consistent with 1, and it's equal to 1 to about 0.25%. The big change was the discovery of this stuff called dark energy. That is, in 1998, it was discovered that the universe is not slowing down under the influence of gravity, which is what everybody involved in me too expected. But rather, the universe has been accelerating in its expansion for about the last 5 billion years. And the mechanism we believe for this is very similar to inflation. Again, it's repulsive gravity driven by a peculiar material, dark energy, which has to be a material with a negative pressure to create this repulsive gravity. The dark energy is causing acceleration at a much, much lower rate than what we think was involved in early universe inflation. But the underlying mechanism, we think, is really pretty much the same. So dark energy not only makes omega turn out to have the right value as predicted by inflation, but it also even provides a clear example of the physics of inflation at work. So that was my second argument for evidence for inflation. And the third one that I want to talk about is the small-scale non-uniformity of the universe. I told you that the cosmic microwave background was uniform to 100 part in 100,000. But at that level, we really see non-uniformities, and now the non-uniformities have been measured to extraordinary accuracy. We know they're there, we know what they look like, where did they come from? There really never was an answer other than the inflationary answer. And the inflationary answer is itself rather remarkable. Maybe I should call this a third miracle even. The inflationary answer is that all the structure in the universe actually arose due to quantum physics. Now we think of quantum physics as being important only on very, very small length scales. Normally, quantum physics is important for atoms, and important for nuclei, but we don't think quantum physics is important for understanding how the table will fall over if I kick it. Classical physics suffices for things like that. But the key thing about inflation, which is bizarre and causes these bizarre effects, is that inflation is constantly stretching microscopic scales, subatomic scales, out to astronomical scales due to this enormous expansion. So what we are seeing in the universe today are the results of quantum fluctuations that occurred on scales far smaller than the size of a proton originally when they actually took place. So inflation can do that. And inflation makes a prediction based on this idea of quantum production of density fluctuations. Inflation makes a prediction for the spectrum of those fluctuations. That is, how should the intensity of the fluctuations depend on wavelength? We measure the wavelength as an angular wavelength on the sky, degrees, but we can talk about a spectrum of what we see on the sky. How intense are the fluctuations as a function of angular scale. And here's a picture of the sky coming from the Planck satellite mission from 2018, which is the latest data set. It's a false color image showing temperature at different pixels on the sky. This oval is intended to be a map of the entire sky, mapped according to some projection. Has a name, but I don't remember it. But it's describing the entire sky on a flat piece of paper. And this is the temperature scale, which, as you see, is in hundreds of microkelvin. And the cosmic background radiation has a temperature of about 2.7 Kelvin. So 1 microkelvin is a part in a million, so this is a part in 100,000, like I said, for how big the fluctuations actually are. They're incredibly tiny, but measured to extraordinary accuracy. So this can be converted into a spectrum. There is Planck's spectrum. The angular scale is shown on the horizontal axis. The largest scales are on the left, smaller scales are on the right. If you know what multiple moment means, it's actually measured as a function of multiple moment, which is slightly better defined than this angular scale, but it's exactly the same thing, really. And that's shown on the top. The dots are the actual measurements, where there are bars going through the dots that are visible. Those are the error bars. And the blue curve is a curve fit to an inflationary model. It's actually a 6-parameter fit, I should admit. There are numbers that go into it that we don't know the values of, so we take them from the measurements. But with 6 parameters, this very complicated curve can be explained, starting from this idea that the density perturbations were generated during inflation as quantum fluctuations, which I think is a very mind-boggling idea and very extraordinarily successful. This is a great fit. Okay, those are the 3 pieces of evidence I wanted to talk about for inflation. The large-scale uniformity, the flatness problem, and the ripples that we see in the cosmic microwave background. Let me move on now to talk about the other topic I want to talk about tonight, the way in which inflation suggests that we live not in a single universe, which is all that exists, but instead in a multiverse, a system of many, perhaps an infinite number of separate universes. I wouldn't say that inflation necessarily implies this, but inflation makes it seem very, very plausible. So here goes. The key fact is that almost all detailed models of inflation lead to this idea of eternal inflation. And the way that happens, roughly speaking, is that inflation is driven by this repulsive gravity material, which I told you is metastable and decays. But decays like a radioactive substance decay. So as you probably know, radioactive substances don't wait for a certain period of time and then suddenly go poof and decay. Rather, each individual atom has just a probability of a half of decaying in any given half-life. Unpredictable when any given atom will decay. Similarly, it's unpredictable when any patch of inflating material will decay. There's just a certain probability per time of the decay happening. And again, it can be characterized by describing it with a half-life. The peculiar thing, though, is that the half-life for the decay is actually it's actually a long period of time compared to the doubling time. So during one half-life, many, many doublings occur. So if you wait for one half-life, if you're following some piece of volume, half of it will decay, but the half that remains will be much larger in volume than what you started with because of the exponential expansion, which outruns the decay. And if the volume that's expanding, that's exponentially expanding, keeps getting bigger and bigger, that never ends. It just goes on forever. And pieces of it decay and become what we call pocket universes in this context. And the backbone keeps going on exponentially expanding. And in the context of our theories, it can do that forever. Although forever is a long time, something might intervene that we don't know about. But as far as we can tell, it goes on forever, producing an infinite number of pocket universes, all for the price of one, which, again, is, I find rather mind-boggling. But it is a pretty clear prediction of these theories. Okay, so I do want to point to one problem that this multiverse can possibly answer, and that I think will be the last topic I'll be talking about. There's something called the cosmological constant problem. I mentioned the cosmological constant maybe twice so far in this talk. I had said that Einstein proposed the cosmological constant back in 1917 because he was trying to build a model of the universe that would not collapse, a static model that would not collapse. And I also mentioned that in 1998, astronomers discovered that the universe was not slowing down, but rather has been expanding for about the past 6 billion years in a process that's very similar to inflation. And that's driven by, we think, the negative pressure material, and we think very likely it is just the vacuum itself. Very likely, this dark energy, whatever it is that's causing the exponential expansion, is just simply a vacuum that has a small positive energy density, and positive energy density is accompanied by a negative pressure and repulsive gravity. And that's the most likely and certainly the simplest explanation for what's going on to account for the observed acceleration of the universe. So that's what I'll assume. So this dark energy, which is by definition just the stuff that's causing the acceleration, is very likely just vacuum energy. So that would say that the vacuum has a positive energy density, which, as I said, goes with a negative pressure. And that would sound very strange to sort of 19th century chemists. A vacuum is just empty. In fact, it sounded strange to Einstein. Einstein never accepted the cosmological constant as being vacuum energy. That's sort of the modern interpretation. Einstein was fundamentally a classical physicist for most of his life. He only helped to invent quantum mechanics in the last years and never quite fully accepted it. But the key issue is classical versus quantum. Classically, you would think of a vacuum as just being empty, and the energy of emptiness should be zero. What else does emptiness mean? But quantum mechanically, the vacuum is viewed as a very complicated state. What makes it the vacuum is simply that it's the lowest possible energy, but the uncertainty principle of quantum mechanics makes any state complicated. So in the vacuum, particle-antiparticle pairs are constantly appearing and disappearing, fields are fluctuating, and in fact we also believe that in the vacuum there's a field that we call the Higgs field, which has a non-zero value throughout space. We need that to explain the behavior of particles that we observe, and we now observe the Higgs particle itself. So it's not at all strange to a particle physicist that the vacuum can have a non-zero energy. However, the value that it has to have to explain the observed amount of acceleration doesn't make any sense to us. It's vastly smaller than what we would expect. We don't know how to calculate the vacuum energy density, so it's all up for grabs. It is an area of uncertainty. But we can make an estimate of what we think it ought to be based on what numbers go into it. And the key peculiarity is that our rough estimates of what we would expect a vacuum energy to look like are much larger than what's observed, and in fact, a full, fantastic 120 orders of magnitude larger than what we observe. So the problem then is, why is the observed vacuum energy so vastly smaller than what we would expect? And that's what's called the cosmological constant problem. Okay. If there's any confusion about the terminology here, cosmological constant and vacuum energy really mean the same thing. They're measured in different units, but they refer to the same thing. The multiverse is a possible answer to that. The idea would go as follows. I'll describe the problem. The idea is that there might not be a unique vacuum to the laws of physics. And in fact, string theory, which many of us regard as the best theory of quantum gravity that we have, maybe the only theory of quantum gravity we have even, string theory does not have a unique vacuum. Rather, it has a colossal number. The original estimate was like 10 to the 500. Now, when I talk to string theorists, they tell me 10 to the 5,000, 10 to the 50,000. Keeps getting bigger. But some more enormous number of possible vacuum-like states. And by vacuum-like, I mean they would look like a vacuum, but they would only be net stable. They would eventually decay, but possibly billions and billions of years before they decay. There's that phrase, billions and billions. I'll say it. Okay. So the idea would be that this vacuum energy, which would differ in each one of these different each one of these different vacuums, they all have a different structure and a different vacuum energy density. And it's important to recognize that this vacuum energy density is not just a label attached to the vacuum. It really affects the way the universe containing that vacuum evolves. That's how we discovered the vacuum energy in our universe, by looking at the acceleration that it drives. So if any one of these bubble universes, pocket universes, if any one of these pocket universes had a vacuum energy as large as what we expect, that, if it was positive, would cause that universe to recollapse in a time of about 10 to the minus 40 seconds. And clearly, no life could possibly form in a universe that just collapses in 10 to the minus 40 seconds. Similarly, if a pocket universe had a vacuum energy of the scale of what we would estimate, but negative, it would fly apart in about 10 to the minus 40 seconds. And again, there would be no time for anything like life or galaxies or any kind of structure to form. So there's a good argument that life would only form in those particular pocket universes that happen to have vacuums in them, which have incredibly small vacuum energies. And when there are this many vacua to choose from, even if the vacuum energy has to be incredibly smaller than average, if you think of these vacuum energies as just being spread over the range of values, there would be plenty that would have this incredibly small vacuum energy. The only problem is to explain why we should be living in such rare universes. And the explanation would be, if this is right, that life only forms in universes that have this incredibly small vacuum energy, and therefore we have an explanation why all living things would observe an incredibly small vacuum energy, even though in the multiverse as a whole, a typical vacuum energy would be 120 orders of magnitude larger. Okay, I guess last sentence just says what I just said. So finally, let me go to the end here, cut to the chase. I just want to end by saying a few words about the acceptance of this idea in the physics community. And this is just a very brief anecdotal summary, but I think telling. At a conference some few years ago, a reporter went around, a science journalist, and asked people how much they would bet on the existence of the multiverse. And I have a few of the answers here on my slides. The first answer I want to give comes from Martin Rees. He is an extremely prominent theoretical astrophysicist. He's the astronomer royal of Great Britain. He's also a former president of the Royal Society of Britain. And he said that he's sufficiently confident about the multiverse to bet his dog's life on. Now, I should admit personally, I've never met Martin Rees's dog, so I'm not sure how cute he is. And Martin would have to feel to him, but I assume that it's a cute dog, and Martin is very attached to that dog. So I think this is a pretty strong bet that Martin's making about it. He has written a number of papers about the multiverse. He does take this seriously. The second person I want to quote is Andre Linde. He's one of my co-founders of Inflation at Stanford University. He, among other things, shared the 2002 Dirac Prize with me and others, the 2004 Google Prize, I think just with me, and the 2012 Fundamental Physics Prize, and the 2014 Kavli Prize. He's also won zillions of prizes, and is a very well-known and highly respected cosmologist, and a huge enthusiast for the multiverse. So he said, he's so confident that he would bet his own life on it. Certainly goes way beyond what Martin Rees was going to say. Not just his dog, but himself. So finally, I just wanted to show you one more quote here from Steve Weinberg, who won, among other things, the Nobel Prize in Physics in 1979. I always regard Steve, by the way, as the voice of reason. If you want to read a great book about cosmology, by the way, I read the first 3 minutes by Steve Weinberg. It's a fabulous book. It's rather old, but nonetheless, almost everything in it is still exactly true, as far as we know. Weinberg did a great job of sorting out ideas that would stick and ideas that would go away. And it's a very well-written book. Anyway, he said he has just enough confidence in the multiverse to bet. Try to think of something clever. He said he has just enough confidence to bet the lives of both Andre Linde and Martin. So I'll stop at that. Thank you.
Okay, we'll take questions from the audience. Just, if you have a question, just raise your hand, and I'll. Yep.
Great talk. Thank you so much. I was just wondering, could you explain a little more about why you need strings to produce this number of vacua that you need to explain the cosmological constant?
Okay, so you're asking about the number of vacua in string theory, and you're asking me more or less why does it have so many vacua?
Yeah, how are those related?
Okay. You're asking me why there are so many vacua, or why that's relevant to inflation?
Why is relevant to the string theory? Why having so many vacua related to string theory?
Okay. So maybe I'll try to answer two things. String theory leads to so many vacua, largely because of the fact, which maybe you've heard, is that the natural number of dimensions in string theory is not 3 plus 1, 3 space plus 1 time, which is what we observe around us, but rather string theory likes 10 plus 1. And that means that if string theory is going to explain our vacuum, the world around us, these extra dimensions have to undergo what is called compactification. And what that means is the extra dimensions essentially curl up into little balls. So if you have, for example, one extra dimension, you can imagine that maybe that extra dimension behaves periodically. So if I go a certain distance this way, I end up on the other side. And then you have to further imagine that the distance involved there is incredibly short, so I don't notice that the dimension exists at all. And in string theory, one has to do that for, I guess, 7 dimensions. Roughly speaking, there's something vacuum because there are many, many different ways these extra dimensions can twist together to leave 3 plus 1 large dimensions. It's really slightly more than what I just said. Once these dimensions are curled up, it's also possible that there are what are called flux lines that run around these closed loops. And we have a whole complicated set of those. So that's roughly speaking the reason why string theory has so many vacua. And the reason it's relevant to inflation and this cosmological constant problem is that each one of these vacua, because they really are made out of different things, would have its own vacuum energy. So instead of trying to find a way to predict that the vacuum energy should be 10 to the minus 120 in the appropriate units, all you have to predict is that 1 out of 10 to the 500 different choices happens to be that small. And that's a much more plausible thing, and becomes, in fact, rather plausible if you accept the assumptions of string theory that all of these vacua are real and any one of them could serve as a substrate for a universe.
You look like you want to ask a question.
I have a question. Hi, my name is Clara. I'm not a physics student. I have no physics background.
Okay.
But I saw you being interviewed and through the wormhole when I was a child, and it greatly influenced the trajectory of my life. So thank you for being here.
Okay.
My question for you is, I understand there's a lot of pushback sometimes to the idea of cosmic inflation because there's no way to verify or measure it through scientific experiments. Correct me if I'm wrong. Especially in the case of the multiverse. What would you suggest would be the next step?
Okay. Okay. Well, we want to distinguish between the multiverse and inflation itself. The multiverse is certainly very hard to verify. I'll say something about that in a minute. But starting with just plain inflation, I think the kind of things that you're talking about come, for example, from a Scientific American article that appeared in 2017, if I remember right, by Starnhart, Loeb, and Ijas. If you're a diligent reader of Scientific American, you would also discover that a few months later there was a letter to the editor signed by 32 physicists who really were all the top leaders of cosmology groups around the world, and included 5 Nobel Prize winners, saying that they categorically disagreed with that article that appeared in Scientific American. Paul Steinhardt has his prejudices, but in my opinion, and I think really the opinion of most of the community, I'll cite some numbers. The 3 pieces of evidence that I talked about for inflation, which are, there are a few more I could have talked about, but they'd be more technical, so we didn't. Those pieces of evidence are very, very convincing. And I think it's just not fair at all to say that inflation cannot be tested. It's total nonsense, I believe. And in terms of the scientific community, one thing you might want to do, I can recommend, if you want to sort of sample how seriously the scientific community takes inflation, is to go to the main particle physics database, the literature database called INSPIRE, and you could type find keyword inflation. It'll give you all the papers for which one of the keywords is inflation, and I think there are about 15,000. So within the scientific community, I think there's essentially nobody who takes this Scientific American article seriously. But there is some controversy, you're right. And one does have to sort things out and maybe decide for yourself what you think you believe. Let me come back to talk about the multiverse, because that, of course, is very hard to test. And certainly right now, what I say is that inflation hints at a multiverse. I certainly do not say inflation implies a multiverse. But it is true, actually, that many individual models of inflation, and by model of inflation, I mean a specific designation of the fields that are involved in driving the inflation. I didn't really talk about the underlying mechanism, but inflation is driven by fields that have certain equations of motion, which we don't know really, we just hypothesize different possibilities. Any particular hypothesis does